If you left Earth right now, traveling faster than any human in history, it would still take you over 70,000 years to reach the nearest star. That fact alone changes everything we think we know about space exploration. Your entire life, every breath, every memory would pass before you covered even a fraction of the distance. So this is not a story about how far we dream of going. It is about how far you could actually travel within a single human lifetime. Tonight, I'll show you the exact point where a human life simply runs out and why it is impossible to go any further. Before we face that limit, if you find value in these deep space videos, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. We like to ask space for distance, how far, how deep, how long. But space doesn't answer in kilometers or miles. Space answers in something far more personal. Time. Because the first wall we collide with isn't a planet, or a star, or a rocket equation. It's a clock, and it's ticking inside our own bodies. The uncomfortable truth is simple. In space, distance is not what stops us. Our lifetime does. And until we define that lifetime with cold, modern numbers, every dream of how far is just mist. So before we ever measure the void, we have to measure us. Across the world, in the most recent United Nations population estimates, global life expectancy at birth is about 73 years. 73. It sounds almost generous until we translate it into what it really is. 73 years is not 73 years of strength, not 73 years of mission readiness, not 73 years of endurance under radiation, isolation and failure. It's simply the average length of a human life measured across billions of different lives, across disease, poverty, accidents and wars. And even within that number, the World Health Organization draws a sharper line. Healthy life expectancy, the years we can expect to live in full health, is closer to about 62 years. That gap matters, because space does not care how old we are. Space cares how resilient our tissues are, how fast our bones thin, how reliably our immune system repairs us, how long our heart stays patient. And the moment we leave Earth's protective cocoon, the universe begins charging interest on every day we spend out there. So we need to be precise, not pessimistic, precise. When NASA talks about astronauts, it doesn't speak in poetry. It speaks in requirements, medical standards, and brutal practicality. NASA's own guidance makes something clear. There is no formal age restriction, but historically, astronaut candidates selected have ranged from their mid-20s to their mid-40s, with an average in the mid-30s. That is not a cultural preference. That is biology, disguised as policy. Because a mission doesn't begin when the rocket launches. A mission begins years earlier. Training, simulations, medical screening, engineering work, team integration, problem rehearsal. Then it continues afterward. Recovery, health monitoring, long-term effects. So the spacefaring human lifespan is not the same as the human lifespan. It's narrower. It's a window where we are skilled enough, strong enough, and medically robust enough to survive long-duration flight. NASA even specifies that astronaut candidates must be able to pass a long-duration spaceflight physical. That phrase sounds clean, clinical. But what it really means is this. Spaceflight is not a trip. It is controlled damage, managed carefully enough that we can keep working while it happens. So when we ask, how far could humans travel in one lifetime? We're not really asking about the full arc from cradle to grave. We're asking about a more fragile currency, the years we can spend inside a mission without the mission consuming us. Imagine this. Picture a single hourglass on a table, but the sand isn't endless. It's not symbolic. It's your total supply of usable, mission-ready time. Now imagine we take a handful of that sand, years of education, training, selection, preparation, and we pour it out before we ever move an inch away from Earth. Then, after the mission, we lose more sand to recovery, rehabilitation, and the long biological echo of microgravity. What remains is what we actually have for travel. And suddenly the question changes shape. It stops being romantic. It becomes mathematical in the most human way. How much sand can we afford to spend just getting there? Because the universe is not charging us in fuel alone. It is charging us in years. Here is the strange part. When people imagine deep space travel, they usually imagine the obvious threats. The cold, the radiation, the loneliness, the failure modes, all real, all terrifying. But even if we solved every single one, perfect shielding, perfect life support, perfect psychology, we would still face the same silent limiter. Travel time, because travel time behaves like a thief. It steals quietly, one day, then another, and it doesn't care how advanced our machines are. If a journey takes 20 years, then it takes 20 years, and no technology can refund those years back into our blood. This is why time dominates all other constraints. Not because the other constraints are easy, but because time is the only one we can't negotiate with. We can bring more redundancy. We can bring better computers. We can bring better medicine, but we cannot bring a second lifetime. And right here, the human mind reaches for a loophole, a beautiful one. Einstein's universe gives us a seductive idea: time dilation. The faster you move through space, the more slowly your time passes compared to someone who stayed behind. Time itself begins to fracture into different rates. That sounds like the escape hatch we've been waiting for. It sounds like a way to cheat the lifetime problem, to travel farther, without spending as much time. And yes, this is not science fiction. It is experimentally verified reality. Scientists have flown precise clocks around the world and watched them disagree with clocks that stayed on the ground, consistent with relativity. NIST, America's National Institute of Standards and Technology, has measured time dilation with atomic clocks so sensitive they can detect differences across small changes in height and gravity. Relativity is not a metaphor, it's a measurement. But then the universe delivers the catch, because time dilation only becomes a meaningful escape when we are moving at a meaningful fraction of the speed of light, and with the speeds humans can actually achieve today. Time dilation is real, but it is almost heartbreakingly small. Consider the most famous human example people point to: NASA's year-long stay on the International Space Station, an orbiting laboratory that moves around Earth at tremendous speed, fast enough to circle the planet in about 90 minutes. To our instincts, that feels like the kind of speed that should twist time. But physics is not impressed by instinct. At that orbital speed, the effect exists, but it barely whispers. A scientific analysis discussing the Scott Kelly mission, about 340 days in orbit, estimates the total time difference from velocity-based time dilation at roughly 1/100th of a second over the whole mission. 1/100th of a second. That is not a new lifetime. That is not a door to the stars. That is the blink you don't notice. So yes, Einstein gives us time dilation, but at human achievable speeds it doesn't save us. Not yet. And this is where everything changes. Because it tells us something brutal about the shape of the problem. If time dilation can't significantly extend our lifetime at the speeds we can realistically reach, then our lifetime remains fixed. And travel distance becomes a simple consequence of that fixed limit. So let's frame it the way space forces us to frame it. Our lifetime is a budget. Every mission spends from it. Every day in transit spends from it. Every delay spends from it. Every slowdown spends from it. And here is the cruel geometry of space. Most destinations are not hard because they are far. They are hard because we have to spend years simply crossing the emptiness. In everyday life, distance feels conquerable because our world is dense. Cities are close, resources are close, help is close. But space is mostly nothing. The gap between worlds is not like a road. It is like an ocean with no shore in sight. And the moment we leave Earth, the clock becomes the real navigation system, not a compass, not a map, a countdown. And now, just for a moment, place yourself inside that reality. You are not watching a rocket launch. You are watching a calendar. You are watching birthdays pass in a habitat the size of a small home. You are watching your own body slowly negotiate with microgravity and radiation. You are watching the years that could have been decades on Earth become transit. And this is the thing most people never fully feel. In deep space, the question isn't, will we get there? The question is, will we still be ourselves when we arrive? Because time doesn't just pass. Time changes us. So when we ask, how far could humans actually travel through space in one lifetime? We now have the first hard boundary. A modern statistical human life is roughly 73 years. A modern healthy lifespan is closer to the low 60s. And the mission-relevant window, the years when we can realistically train, launch, endure, and return, is narrower still, shaped by physical demands and medical screening. Time dilation is real, verified, measurable, but at the speeds humans have actually travelled, it barely moves the needle. So the clock remains the ruler. And that means the next question is unavoidable. If time is the budget, then speed is the only way to buy more distance. But speed has its own law, a law written into the structure of reality itself, a speed limit that doesn't care about our ambition. And once we see it clearly, we begin to understand why the universe feels so close and yet stays so far. Because what comes next is not an engineering problem first, it's a physics problem, and physics does not negotiate. There's a moment every time we talk about deep space when the conversation turns into a quiet act of denial. Because once we accept that a human life is a finite budget, the next instinct is obvious. We try to buy more distance with speed. We imagine faster engines, stronger rockets, a future where we simply outrun the problem. But then the universe reveals something disturbing. It isn't just that space is big, it's that reality itself has a speed limit. Not a policy, not a technological hurdle, a law. And it's written so deeply into the structure of nature that even light obeys it. The speed of light in vacuum is roughly 299,792 kilometers per second, about 186,000 miles per second. Let that land for a moment. That is fast enough to circle Earth more than 7 times in a single second. Fast enough that if you blink, light has already crossed the United States and back again, and still had time left over. And yet, even that cosmic velocity is not fast by the standards of the universe. It's just the maximum allowed. Because the speed of light isn't only the speed of light, it's the speed at which cause and effect can propagate through space-time, the speed at which reality can pass a message to itself. And that's why Einstein's special relativity doesn't treat it as a suggestion. It treats it as a boundary, a hard edge. Here's the strange part. Most speed limits we know are negotiable. A car can exceed the number on a sign. A plane can fly faster than its usual cruise. A bullet can be engineered to move faster. But this speed limit isn't painted on asphalt. It's built into the geometry of space-time. Special relativity tells us that no material object can be accelerated all the way to light speed. Not because we lack will, not because we lack engineering, but because something inside the physics begins to behave monstrously. As we approach that limit, nature starts charging an escalating price for every additional fraction of speed. And it isn't linear. It doesn't feel fair. It feels like the universe is tightening a fist. In theory, light speed is the ceiling, but in practice, we live far below it. Even our most extreme human-made accelerators, machines built to push particles to staggering velocities, only approach the limit, never touch it. The Large Hadron Collider, for example, accelerates protons to 99.9999991% of the speed of light. That number looks like victory, It looks like we're basically there. But the truth is more unsettling. That last tiny sliver, the difference between almost and equal, is where the cost becomes catastrophic. It's where the math stops being polite. It's where the universe makes an example out of ambition, because near light speed, a little faster doesn't mean a little more energy. It means a vastly greater amount of energy for an almost invisible gain in speed. This is why we must distinguish between what is allowed in principle and what is achievable in a human lifetime, with a human civilization's resources. The ceiling might be light speed, but our real limits sit far below it, and the closer we get, the more reality resists. Imagine this. Picture a staircase in a dark hallway. At first, climbing feels normal. Each step costs you effort, but it's predictable. Then halfway up, the steps start changing. Each new step becomes taller than the last. You lift your leg higher, your lungs strain, your muscles begin to burn. And near the top, the staircase doesn't even look like a staircase anymore. It becomes a vertical wall. You can still reach upward, you can still try. But now, every extra centimetre requires a ridiculous, exhausting leap. That is what approaching light speed is like. Early gains are expensive. Later gains become punishing. Near the limit, the cost becomes effectively unpayable. Einstein's relativity doesn't say you can't go fast. It says something more precise and more disturbing. As an object with mass accelerates toward the speed of light, the energy required to keep accelerating it keeps rising without letting up, until at the limit, the required energy becomes effectively infinite. That word, infinite, is not poetry. It's physics, expressing a real impossibility. It means there is no engine, no fuel tank, no civilization, no star you can burn like coal that can supply enough. Not if the goal is to push a massive object to exactly light speed. And what makes this truly disturbing is that the universe enforces this rule even on the smallest things we can manipulate. Even in the Large Hadron Collider, even with protons, particles so small we can't see them, the machine can push them to almost light speed, but never to light speed. The closer they get, the more the added energy goes into the system, and the less it shows up as extra speed. It's like pouring effort into a flame that refuses to grow brighter. In everyday life, doubling speed feels simple. Ride a bicycle faster. Press the gas pedal harder. Our minds expect speed to respond smoothly. But near light speed, kinetic energy does not behave like that. At low speeds, energy and velocity feel linked in a way our bodies understand. But as we climb toward relativistic speeds, the relationship begins to warp. The energy cost starts rising faster than the speed itself. It becomes non-intuitive, violent, disproportionate. And that's the core trap hidden inside the dream of interstellar travel. We can always imagine just going faster. But nature doesn't let us just do anything. Not near the boundary. Because the last stretch toward light speed isn't a road, it's a wall. This is not just theory. Relativity isn't believed because it's elegant. It's believed because it survives tests that were designed to break it. The speed of light isn't an estimate. It's a defined constant in our measurement system. And the deeper implication that light speed is a universal limit for matter, energy transfer, and information appears across authoritative explanations of special relativity. Even the way our measurement of distance is defined now is quietly haunting. We define the meter using the speed of light, meaning the speed limit isn't merely a number in a textbook. It is part of how we describe reality with language and measurement. The limit is built into our rulers. And now, for just a second, place yourself inside the temptation. You're in a spacecraft, a small human habitat surrounded by perfect darkness. You feel the hum of systems keeping your lungs supplied with oxygen. And you ask a simple question: if we just go faster, how far could we go before our life runs out? This is where the story cracks open, Because faster isn't a dial we can turn forever. It's a negotiation with the deepest law we've ever discovered, and the universe doesn't compromise. So what do we do with this? We accept something uncomfortable. The cosmic speed limit means time cannot be beaten simply by wishing for more speed. Not for human-scale missions, not for human bodies, not for a civilization that must carry fuel, shielding, life support, redundancy, and still accelerate. The limit doesn't just stop us from reaching light speed, it stops us from getting anywhere near it with anything large, alive, and fragile. And that means our reachable distance in one lifetime is not set by imagination. It is set by how fast we can actually push a crewed vehicle, using propulsion that obeys physics, mass, and energy constraints. Which leads us to the next unavoidable truth. If speed is limited by reality, then propulsion is not just engineering. Propulsion becomes destiny. There's a brutal honesty in letting history answer for us. Not our hopes, not our concept art, not the clean confidence of future promises. History. Because if we want to know what speed really means for a human lifetime in space, we have to start with one uncomfortable fact. Humans have already gone as fast as we've ever gone, and it happened more than half a century ago. Not in some distant, hyper-advanced era, but in an age of slide rules, room-sized computers, and rocket fuel that burned like controlled lightning. And that should bother us, because it suggests the barrier isn't only imagination, it's physics and cost, and the heavy, punishing reality of mass. So let's measure speed the way the universe measures it, not by what we want, by what we've done. Most of us have felt fast, a highway at night, a plane at cruising altitude. The world becomes smoother, the noise changes, the ground turns into a blurred texture. But those speeds are gentle. They are small. In low Earth orbit, the International Space Station is moving at about 5 miles per second, around 17,500 miles per hour, about 28,000 kilometers per hour. 5 miles per second. Let that sit in your chest. That's fast enough to cross a city before your mind can fully register the motion. Fast enough that up there, sunrise and sunset happen every 90 minutes. And yet, even that astonishing velocity is only the beginning, because orbit is not the record. Orbit is the warm-up. To understand how fast humans have travelled, we have to separate 3 different kinds of speed, because space doesn't care about one number, it cares about context. First, orbital speed. Orbital speed is what keeps you from falling. You're moving sideways so fast that as gravity pulls you down, Earth curves away beneath you. It's a knife-edge balance. That's the station's world. About 17,500 miles per hour, 28,000 kilometers per hour. Second, escape speed. Escape speed is what frees you. It's the speed required to break Earth's gravitational hold, about 11.2 kilometers per second, roughly 25,000 miles per hour at Earth's surface, ignoring air resistance. That's not faster travel. That's a different category of existence. It's the difference between circling your home and leaving it. Third, interplanetary transfer speed. This is where things become unsettling, because once you're out there, once Earth is no longer your anchor, the important question becomes, how fast can you carry a living human body across the emptiness between worlds? And here, history gives us an answer that hasn't been beaten. The fastest humans have ever travelled, relative to Earth, was during Apollo 10. On May 26, 1969, returning from the Moon, the crew reached about 24,791 miles per hour, about 39,897 kilometers per hour. That's roughly 11 kilometers per second, a number so large it almost stops feeling like speed and starts feeling like weather. A storm moving through space. NASA notes that while lunar missions entered at similar speeds, Apollo 10 set the record for the highest velocity attained by a piloted vehicle. And this is where the story cracks open. Because if human speed was a straight line of progress, We would expect that record to be broken many times by now. But it hasn't. Not by the space shuttle. Not by decades of space stations. Not by modern capsules. Apollo remains the high water mark. And the reason isn't a lack of bravery. It's that Apollo did something we rarely do anymore. It spent enormous energy to send humans beyond Earth. Then it let gravity do the rest on the way home. Imagine this. Picture a child's slingshot. The farther you pull the band back, the more energy you store. And when you release it, that energy becomes motion. Now replace the rubber band with gravity. Earth pulls, the moon pulls, the spacecraft falls through a landscape of invisible slopes. Apollo didn't power its way to that record speed like a jet engine pushing through air. It fell in a controlled way through the gravitational terrain of the Earth-Moon system, then returned with a trajectory that brought it in fast. That speed was the signature of a mission that left Earth's neighborhood entirely. And to do that, we paid a price. Not in poetry, in propellant, in mass, in mission complexity, in risk. Here's the uncomfortable truth. Most crewed spaceflight since Apollo has stayed close to Earth in low Earth orbit. Because low Earth orbit is forgiving. Communication is near instant. Rescue is at least imaginable. Resupply is possible. And the environment, while dangerous, is still within reach of our planet's protection and logistics. But the moment we go farther, truly farther, we need something else. We need energy on a scale that modern human spaceflight has rarely been willing to spend on people. It's easier to send machines. They don't need air. They don't need water. They don't need to come home alive. But humans do. So our speed record still belongs to Apollo, because Apollo belongs to a category we have rarely repeated. Crewed deep space flight beyond low Earth orbit. Now let's do something that feels almost impossible. Place yourself inside that return. You're strapped into a capsule. The window is small. The world outside is black. And then Earth grows. Fast. Not like a plane approaching a runway. Like a planet rising to meet you. At around 11 kilometers per second, about 24,790 miles per hour, you are not arriving. You are colliding with an atmosphere at a speed that turns air into plasma. NASA's own Apollo documentation describes lunar return re-entry as nearly 40,000 kilometers per hour. And suddenly the word speed stops sounding exciting. It starts sounding dangerous. Because at these velocities, even small errors are catastrophic. The margin between survive and burn becomes razor thin, which is why these speeds are not just achievements, they are boundaries. And now we arrive at the real lesson hidden inside these numbers. It's not only that Apollo was fast, it's why that speed is so hard to exceed. As velocity rises, the energy demand doesn't rise gently, it rises brutally. Because you're not only pushing mass, you're pushing mass that needs fuel, and fuel is mass too. So every attempt to go faster creates a deeper problem. To carry more fuel, you need more fuel. To accelerate that extra fuel, you need even more fuel. And soon the mission becomes less like a vehicle and more like a tower of propellant with a small, fragile human habitat perched on top. This is why just go faster is not a simple plan. It's a chain reaction, and it's why, historically, the highest crewed speeds happened during a very specific kind of mission, one where enormous launch energy was invested, then gravity helped shape the return. Apollo didn't make high speed cheap. Apollo made it briefly possible. So what do we know, without guessing, without speculation? We know humans can live in orbit for long durations while moving around 17,500 miles per hour, about 28,000 kilometers per hour. We know humans have escaped Earth and returned at around 24,791 miles per hour, about 39,897 kilometers per hour, the Apollo 10 record. We know Earth's escape speed is about 11.2 kilometers per second, roughly 25,000 miles per hour. A threshold that marks the difference between staying bound and leaving. And we know the moon's escape speed, its grip, is far smaller, about 2.4 kilometers per second, roughly 1.5 miles per second. That last number is quietly haunting, because it tells us something about the universe. Even a world as close as the moon is separated from us by a kind of energetic cliff. And the farther we go, the steeper those cliffs become, not because space is crowded with obstacles, but because it is dominated by gravity wells and the price of climbing out of them. Let's translate Apollo 10's record into something human. At about 24,790 miles per hour, 39,897 kilometers per hour, Apollo was moving fast enough to cross the entire United States in roughly 6 minutes. Fast enough to go from London to New York in under 10 minutes. That sounds like Dominion. But then, space reveals the trap. Even at that speed, if you aimed for the nearest star, Proxima Centauri, more than 4 light-years away, you'd still be travelling for over 100,000 years. That is 10 times longer than everything we call civilization. It is a span of time that reaches back to when Neanderthals were the masters of Europe and the Sahara was a lush green forest. Speed that feels like thunder is still almost nothing against interstellar distance, and this is exactly why our lifetime remains the true ruler. Because even our fastest human speed is not a doorway to the stars. It's barely a stride beyond our home world. Apollo's record is more than a trivia fact. It is a measurement of our real ceiling, given what we've proven with human lives on the line. It tells us that speed is not a fantasy. It's an expense, it's risk, it's mass, it's heat, it's structural limits, it's navigation accuracy, it's life support enduring a harsher environment. And it's the terrifying reality that at extreme velocity there is no gentle failure, only sudden, violent consequence. So yes, humans have gone fast. We've gone faster than a rifle bullet, faster than a meteor crossing the sky, and we did it inside. A capsule no bigger than a small room. But the record still stands, because to go faster than Apollo, we would need to pay a price that grows out of proportion. And that leads us to the next truth, one that decides our reach more than any dream ever will. Speed is not just physics. Speed is fuel. We've felt the speed limit of reality. We've watched human history hit its own record and stop. And now we reach the part of the story that doesn't feel like astronomy at all. It feels like accounting. Because once speed becomes precious, the universe asks a humiliating question. What are we willing to carry to buy it? Fuel, tanks, engines, shielding, air, water, food, spare parts, a habitat that can keep a human body alive while the void tries to dismantle it. And the moment we start adding those things, the dream collapses into a law so unforgiving it has a reputation among engineers like a curse. The rocket equation, not a design flaw, not a temporary limitation, a governing rule of motion for anything that throws mass backward to move forward. And it behaves like this. The more we want to change our speed, the more our vehicle stops being a vehicle and becomes mostly propellant. NASA's own Glenn Research Center puts it bluntly for rockets aiming for orbit. About 90% of the liftoff weight is propellant. 90%. That isn't a machine carrying fuel. That's fuel briefly borrowing a machine. And this is where everything changes. Because once fuel dominates, distance stops being a map problem. It becomes a mass problem. Konstantin Tsiolkovsky, one of the founding thinkers of astronautics, described the brutal relationship between a rocket's achievable change in speed and the ratio between its starting mass and its ending mass. NASA teaches this relationship as the ideal rocket equation, and it emphasizes a feature that sounds harmless until you really feel it. The change in velocity depends on the natural log of the mass ratio. Natural log, mass ratio. These are calm words for a violent reality, because what it means, spoken plainly, is this. To gain more speed, we don't just add more fuel, we must increase the ratio of everything at liftoff compared to everything left after the fuel is gone. And that relationship punishes us. Hard. Imagine this. Picture a child trying to walk to school with a backpack. At first, adding an extra book feels fine, but then someone says, if you want to walk twice as far, you need extra snacks. So you add snacks. But those snacks have weight, so now you need more snacks to carry the extra snacks. Then more water, because you're walking longer. Then an extra jacket, just in case. And soon, the backpack is so heavy the child can't even take the first step. That is the rocket equation in human terms. Fuel is not just cargo. Fuel is the thing you must accelerate. And every kilogram you add must be accelerated by fuel that also has mass, which must also be accelerated by even more fuel. The logic becomes recursive. The math becomes merciless. And the rocket becomes mostly propellant, because the universe won't let it be anything else. Here is the core trap. A rocket's engine doesn't push against air. It doesn't push against the ground. It pushes by, throwing mass away. That expelled mass is called propellant. And NASA's Glenn Research Center explains performance using a concept called specific impulse, a way to describe how effectively an engine uses its propellant to produce thrust. But even with excellent engines, the basic problem remains. If the engine is efficient, we get more change in speed per unit of propellant. If it's inefficient, we get less. But in all cases, the relationship between speed gain and propellant is not gentle. It is not linear. At some point, adding a little more speed requires a disproportionate increase in propellant fraction. And that's when engineers start speaking in a darker language. Mass fraction, mass ratio, payload penalty. Because when propellant dominates, payload becomes what's left over after physics takes its cut, and physics takes a lot. NASA's mass ratio explanation is deceptively calm. It points out that the change in velocity depends on the natural log of mass ratio. That seems manageable until we translate the consequence. A log relationship means the returns shrink. To get the next chunk of speed, you don't double your propellant. You might need far more than that. The rocket equation doesn't scale like a road trip. It scales like an addiction. Each additional gain costs more than the last. And this is why big rockets look the way they do. Long, towering, mostly tanks. Because when we try to push humans beyond Earth, the vehicle must carry not just speed, but the ability to create speed. And that ability has mass. A monstrous amount of mass. Now place yourself in the most honest place imaginable. Not in space. On the launch pad. You're looking up at a rocket and you're trying to see the ship. But what you're really seeing is propellant. You're watching a controlled explosion shaped into a column, and you realize something unsettling. Most of what's above you is not the mission. It's the cost of changing velocity, the price of escaping Earth's gravity well, the price of reaching the kind of speed we talked about earlier. And suddenly, the dream becomes heavier, because now we understand the true nature of the barrier. It isn't courage, it's economics of mass. Let's name the problem directly. A human mission is not a probe. A probe can be small. A probe can be cold. A probe can fail silently. A human mission must be redundant. It must be safe. It must carry life. And every layer of safety is mass. More structure, more shielding, more air, more water, more spare parts, more power systems, more thermal control, then more fuel to push all that mass, then stronger tanks to hold that fuel, then stronger structure to hold the tanks, then even more mass. This compounding is why rockets don't simply get a bit bigger as we raise our ambitions. They balloon, and NASA's note that orbital rockets can be about 90% propellant becomes less like trivia and more like a warning. It's telling us the universe is forcing most of the launch mass to be fuel, because that's what it costs to change velocity on the scale that space demands. So how did we ever do it? How did we ever reach orbit at all? How did we ever send humans to the moon? We used a strategy that feels almost like cheating, except it's also part of the law. Staging. Staging means we deliberately discard mass, empty tanks, used engines, dead weight, so the remaining vehicle doesn't have to keep accelerating what it no longer needs. NASA's beginner materials emphasize staging as a core concept of reaching orbit, and the Glenn site explicitly provides booster staging as a major topic alongside the rocket equation itself. And this is the key. Staging doesn't defeat the rocket equation. It respects it. It plays along. It says, if mass is our enemy, then we must shed mass as we go, like a climber dropping gear to survive the final ascent. Here's the disturbing part. Staging is powerful, but it is not infinite, because every stage we add brings its own penalties. More engines, more structure, more separation systems, more complexity, more failure points. And in human missions, failure points are not inconveniences. They are lethal. So staging becomes a balancing act between physics and reliability. We can throw away mass to improve performance, but each thrown away piece had to be carried up to speed in the first place. And each added stage is another system that must work perfectly. In the vacuum, perfection isn't poetic, it's survival. Now connect this back to the central mystery. We are not trying to build a rocket for a record, we are trying to build a rocket for a human lifetime. That means we are not just chasing speed for speed's sake, we are chasing speed because time is expensive. And yet the rocket equation tells us speed demands propellant, and propellant demands mass, and mass demands more propellant. So the very attempt to shorten travel time can swell the vehicle until it becomes impractical to launch, impractical to assemble, impractical to finance, and, most importantly, impractical to keep alive. This is why propulsion isn't a side detail. It's not a technical footnote. It is the boundary condition for everything. How far we go, how fast we go, how long we survive, how much we can bring, how much redundancy we can afford, how much shielding we can carry. All of it is chained to propulsion and to this mathematical tyranny. NASA's mass ratio framing makes that clear. Velocity change is tied to how much mass we can afford to throw away. So when we ask the question again, how far could humans actually travel through space in one lifetime, we should feel the shape of the answer forming, not as a destination, as a constraint. The rocket equation doesn't tell us where to go. It tells us what we must pay to go anywhere, and it tells us, with quiet brutality, that most of our mass will always be fuel, especially when we start from a deep gravity well like Earth's. That means our reachable distance is not just about courage, not just about engineering. It's about mass fractions and propellant budgets that swell until the mission becomes mostly the act of moving its own fuel. And that creates the next unavoidable question. If the rocket equation governs our reach, if staging only buys us so much, then what can we truly do with the propulsion we already know how to use reliably? Because once propulsion sets the rules, propulsion defines reachable distance. We can feel the truth forming now. A lifetime is finite. Reality has a speed limit. Our fastest human journeys still live close to Earth, and the rocket equation stands behind all of it like a quiet judge, counting mass, counting fuel, counting every kilogram we dare to carry. So now we arrive at the engine we actually know, the engine that took us to orbit, the engine that took us to the moon, the engine that still lifts almost everything we launch today. Chemical propulsion. It sounds ordinary, almost old-fashioned. But chemical rockets are not primitive. They are violent miracles of controlled fire, built to turn molecular bonds into motion. And yet, that is exactly the problem. Because chemical fire is powerful, but it is also fundamentally limited. Not by politics, not by courage, by chemistry itself. A chemical rocket is a bargain with nature. We store energy inside the bonds of molecules, then we break those bonds violently inside a chamber. Hot gas expands, and the rocket escapes by throwing that gas away. This is why chemical propulsion feels so immediate, so primal. It's not exotic physics, it's combustion. But this also means chemical rockets are trapped inside a ceiling. The energy per kilogram of propellant is limited to what chemical bonds can provide. And the best chemical engines, the kinds NASA has studied and flown, reach vacuum performance in the neighborhood of the mid-400s in specific impulse for liquid oxygen and liquid hydrogen class engines. That number matters, but we don't need to worship it. We only need to understand what it implies. Chemical propulsion is astonishing, and still not enough to make the solar system feel small. So what can we reach inside one human lifetime using propulsion we already understand and can build? The honest answer is not the stars. The honest answer is not even the outer planets. The honest answer is a smaller, harsher sphere, a sphere defined not just by distance, but by time. Because chemical rockets don't just decide how far we can go, they decide how long we must endure the emptiness to get there. And this is where the story turns from romance to logistics. Mars is the great temptation, close enough to dream about, far enough to punish us for dreaming carelessly. In the most energy-efficient trajectories, the ones missions are usually built around, getting to Mars is not a weekend. It's not even a season. NASA-connected planning literature and mission studies commonly assume roughly 6 months of cruise time each way for human-class mission profiles. And in the broader public discussion of Mars transfers, a typical Earth-to-Mars HOMAN transfer time is often described as about 9 months. So even before we land, we've already spent something precious. Months of life support, months of exposure, months of isolation, months of watching Earth shrink into a bright star you cannot touch. And this is only the beginning, because Mars is not a place you can drop by. Mars is a world that forces you to obey orbital geometry. Here's where the universe becomes maddeningly specific. Earth and Mars are not standing still. They are running on separate tracks around the Sun, and the alignment that makes a trip efficient, an alignment that saves propellant and makes mission design sane, doesn't happen whenever we want. It happens on a cycle of about 26 months. NASA itself describes this cadence clearly. About once every 26 months, Earth and Mars are positioned for the most energy-efficient trip. 26 months. That means if we miss the window, we don't wait a week. We wait years. So the trip isn't just how long to get there, it's how long the entire mission must be shaped around these windows. And that changes everything. Because for humans, the mission is not only the outbound flight, it's the outbound flight, plus the stay, plus the return, plus the fact that the universe will not let us choose those segments independently. NASA's Human Mars Reference Architectures describe broad mission classes that reveal the real constraint. Some missions are built for shorter stays on Mars, on the order of 30 to 90 days, with total round-trip times around 500 to 650 days. Other mission concepts assume much longer surface stays, around 500 days, because the return window geometry often makes it practical to wait rather than spend enormous propellant forcing an early return. Either way, we're not talking about travel. We're talking about an expedition measured in years, and those years are not spent exploring pristine landscapes the whole time. They are spent maintaining life, managing risk, repairing systems, protecting bodies from environments humans did not evolve to survive. So Mars becomes the practical outer edge, not because it's the farthest place we can imagine, but because it's the farthest place where the total mission profile can still plausibly fit inside a human life, without becoming a multi-decade sentence. Chemical propulsion can take us to Mars, but it cannot make Mars quick. Imagine this. Picture a long nighttime highway. You're driving through darkness, and there's one exit you must take, but the exit only appears once every 26 months. If you arrive too early, it isn't there. If you arrive too late, it's gone. So you don't drive when you feel ready. You drive when the road allows it. That's what Mars launch windows feel like in mission planning. The universe schedules the trip. We just try to arrive on time, and once we accept that, we understand why distance alone is a misleading metric, because a destination can be close in kilometers and still be far in years. Now we can state the limit without exaggeration. Chemical rockets can push us out of Earth's gravity well. They can put humans on the moon. They can plausibly carry humans to Mars. But when we push beyond that, toward the outer planets, the travel times at chemical propulsion class velocities start to exceed what a human lifetime can comfortably spend in transit and survival mode. And the rocket equation returns like a shadow. If we try to shorten those travel times by adding more propellant, we swell the spacecraft until it becomes less like a ship and more like a fuel structure that must lift its own fuel. We don't just run out of speed, we run out of mass margin, we run out of practical launch architectures, we run out of the ability to protect and sustain humans for the durations imposed by the physics. So chemical fire draws a boundary, not because it is weak, but because it is chained to chemistry, and chemistry is chained to finite energy. Now place yourself inside the honest version of this journey. Not the poster, not the montage. You are months into transit. The walls around you are thin compared to the emptiness outside. The sounds are recycled air and machinery. You mark time not by sunsets, but by checklists, and you realize something unsettling. Even if Mars is reachable, the trip itself becomes the dominant event of your life. Not the landing, not the first footprint, the passage of time. This is what chemical propulsion forces us to confront. We can cross the distance, but we cannot escape what the distance does to us while we cross it. So when we ask, how far could humans actually travel through space in one lifetime? Chemical propulsion gives a grounded, historical answer. Our realistic human sphere, using propulsion we already know how to build and fly, is the inner solar system, Earth, the Moon, and, at the outer edge of practical human timelines, Mars, because even Mars demands launch windows, long transits, and mission architectures measured in years. And this creates the next problem, because once chemical limits are reached, wishing doesn't help. Only a different kind of propulsion changes the equation, not by breaking physics, but by changing what kind of energy we carry. Because when chemical fire runs out of leverage, alternatives emerge. Chemical fire carries us like a heartbeat, violent, immediate, familiar, but it also cages us inside a cruel trade. Every extra day we want to save in travel time demands a swelling sacrifice of propellant, and eventually that sacrifice becomes absurd. So our minds reach for a different kind of power. Not a hotter flame, not a bigger tank, something fundamentally denser, something that doesn't borrow its strength from chemical bonds at all, something that borrows it from the nucleus. Because inside the nucleus, nature hides an energy scale that makes chemical fire look like a candle, and this is where the temptation becomes almost unbearable. If we bring nuclear energy into propulsion, do we finally break free? We can't break physics, but maybe we can change the terms of the prison. But then the universe delivers the familiar twist. Nuclear propulsion can make us faster. It can make the solar system feel less like an ocean, but it cannot make a human lifetime infinite. And that means nuclear propulsion offers a powerful upgrade without granting the one thing we truly want: time. When people say nuclear rockets, they often imagine one thing: a single engine, a single concept. But in reality, there are two very different paths, with two very different personalities. One is loud and direct, the other is quiet and patient. Nuclear thermal propulsion. This is the closest nuclear propulsion comes to feeling like a traditional rocket. A reactor heats a propellant, typically hydrogen, and the hot gas expands through a nozzle to create thrust. The key advantage is not magic, it's efficiency. Nuclear heat can drive the exhaust to higher effective performance than chemical combustion can, because it isn't limited by chemical energy density. NASA presentations summarizing space nuclear propulsion explicitly frame nuclear thermal propulsion as a nearer-term concept for higher performance rockets, including its connection to efforts like the Draco flight, demonstration concept, nuclear electric propulsion. This looks completely different. A reactor generates electricity. That electricity powers electric thrusters, often ion or Hall effect systems, that accelerate propellant to extremely high exhaust speeds. The thrust is gentle, almost ghost-like, but it can run for a very long time, steadily building up velocity. NASA has decades of electric propulsion development, including the next ion thruster program, with a world record endurance test exceeding 48,000 hours of operation. So, nuclear thermal is the hammer, nuclear electric is the tide. Both can change how we move through the solar system, but neither changes the core truth. We still have to survive the journey. Here's where credibility matters, because nuclear propulsion is surrounded by dramatic imagery, but our job is to stay anchored to what has actually happened. Nuclear thermal propulsion has been tested on Earth. In the 1960s, the United States ran major ground test programs under the rover and Nerva efforts at the Nevada test site, using dedicated facilities to assemble, test, and handle nuclear rocket engines. NASA's technical history of nuclear thermal propulsion testing describes the infrastructure and the reality of those engine tests. Hot hydrogen flowing through a reactor core, producing thrust-class operation in ground conditions. What has not happened is just as important. A nuclear thermal rocket has not yet flown in space as an operational propulsion system for a mission. The work exists, the physics is real, but the leap from ground test to flight is a different category of difficulty: engineering, safety, regulation, mission architecture. Nuclear electric propulsion has been proven in space without nuclear power. Electric propulsion itself is not theoretical. Ion thrusters have flown on science missions. NASA's next thruster, for example, achieved a multi-year endurance record in ground testing, demonstrating the kind of long-life operation electric propulsion is designed for. But nuclear electric propulsion, specifically a fission reactor generating the electricity for deep space electric thrust, is rarer in modern practice. Still, nuclear power in space is not imaginary. The United States flew SNAP-10A in 1965, the only US mission to operate a fission reactor in orbit. It produced electrical power for weeks before a non-nuclear electrical issue ended the mission. That detail matters, because it proves a foundational piece. Reactors can operate in space, but it also exposes the other truth. Space doesn't fail only at the reactor. Space fails in the wiring, the regulators, the mundane components that are forced to perform perfectly for years. So we have this strange split. We have tested nuclear thermal propulsion on Earth. We have demonstrated nuclear power in orbit. We have flown electric propulsion systems and pushed their lifetime limits. But weaving those threads into a routine, crude, nuclear-propelled deep space capability is still a frontier. Not because it violates physics, because it demands perfection in an unforgiving place. Imagine this. Picture a massive boulder in your driveway. Chemical propulsion is like trying to shove it with one violent push. It works, if your push is strong enough. But the energy comes in a brief, brutal burst. Nuclear thermal propulsion is like replacing your muscles with a powerful machine that can shove harder per kilogram of fuel you carry. You still push, you just get more out of what you bring. Nuclear electric propulsion is different. It's like attaching a winch and slowly pulling the boulder, millimeter by millimeter, day after day. The pull feels weak in any single moment, but over time, it changes everything. That's the difference. Nuclear thermal, higher thrust, higher performance, shorter burns. Nuclear electric, low thrust, long duration, deep efficiency. Both are real. Both are limited. Now we face the question that always arrives here. Does nuclear propulsion let us race through space? Not like science fiction, not like light-speed dreams, but realistically, how much faster can it make our journeys? We need to speak carefully. Nuclear thermal propulsion is often described as offering roughly about twice the efficiency of chemical propulsion in terms of specific impulse for comparable mission roles, an idea repeated across historical Nerva-era assessments and modern summaries, and echoed in discussions of why it was attractive for deep space missions. But that does not mean twice as fast to anywhere, because mission time isn't only engine efficiency, it's trajectory design, it's how much mass we're carrying, it's whether we're optimizing for minimum energy or minimum time, it's heat rejection, it's safety margins, it's the rocket equation still whispering in the background. Nuclear electric propulsion is even more misunderstood. It can achieve extremely high exhaust velocities, and NASA's next thruster materials describe xenon ions accelerated to extremely high speeds, enabling dramatic improvement in performance compared to chemical engines. But electric propulsion doesn't give you big acceleration, it gives you endurance. It's a marathon engine. So nuclear propulsion can improve travel times for certain mission profiles. It can widen what's feasible, but it does not unlock the fantasy of human travel to the stars. It makes the solar system more navigable, not small. Let's translate the scale the way our bodies understand. NASA's electric thruster reporting notes exhaust-related performance, capable of propelling ions to speeds up to about 90,000 miles per hour. About 145,000 kilometers per hour. 90,000 miles per hour. That sounds like a planet-killer speed. At 90,000 miles per hour, you could go from Los Angeles to New York in under 2 minutes. And yet, if you aimed that kind of capability at interstellar distance, at even the nearest star, the journey would still take over 30,000 years. We call this speed stunning because it crosses continents in minutes. But against the void, it is a crawl. If we had launched such a ship when the first cave paintings were being etched in France, it would only be arriving now. Not because the engines are weak, because interstellar space is vast beyond the scale our nervous system can truly hold. So nuclear propulsion changes the grade of the hill, but it does not remove the mountain. Now let's bring it back to the question we're truly answering. One lifetime, one clock. Nuclear propulsion can reduce travel time within the solar system. It can make rapid movement in cislunar space and deep space more practical. Exactly why programs like DARPA's Draco concept were framed around agile operations beyond Earth orbit, paired with NASA engagement on nuclear thermal propulsion demonstration goals. But even if we imagine mature nuclear propulsion systems enabling faster transits, the human constraint remains. Multi-decade travel is not just a navigation problem, it is a life problem. A decade is not a long trip. A decade is a transformation. It's the difference between being 30 and being 40, between one immune system and another, between one body and the body that comes after years of exposure to microgravity and deep space radiation. So when we translate nuclear propulsion into decades, we get a sober picture. Within a decade, we can imagine robust human expeditions within the inner solar system becoming more flexible, more resilient to launch window tyranny, more capable of carrying shielding and redundancy because the propulsion burden shifts. Over multiple decades, even if the ship can keep moving, the human mission begins to drift from travel into survival. And this is the part people resist, because it feels like the universe is being cruel. But it isn't cruelty, it's simply scale. Now place yourself inside the real version of a long nuclear-propelled voyage. You wake up to the same hum, the same recycled air, the same soft vibration of machinery. The calendar pages are not dramatic, they are quiet. And you realize something that changes the emotional meaning of distance. Even if the spacecraft is still working, your body is still spending your lifetime. You are paying for every kilometre with months of biology. And that's when the central mystery tightens. Nuclear propulsion can buy us speed, but it cannot buy us youth. So what do we say, honestly? Nuclear propulsion is not fantasy. Its foundations have been tested. Nuclear thermal rocket engines were built and fired on Earth in major historical programs. Electric propulsion systems have demonstrated extreme endurance and performance in NASA testing. A US fission reactor has operated in orbit, proving space nuclear power is physically possible. But the promise is specific. Nuclear propulsion can help us move faster in the solar system. It can reduce some transit times, it can expand what is plausible. It can make Mars missions less trapped by the slow rhythm of chemical fire. Yet it cannot defeat the deepest limiter we started with. A human lifetime still runs, and even a fast ship does not erase the time it takes to cross emptiness, which leaves us with the next unavoidable truth. Even if propulsion improves, propulsion is only half the story. Because the other half is the fragile passenger. And to go farther than chemical fire ever comfortably allowed, humans must survive. We can build faster ships, we can carry denser energy, we can even dream in nuclear light. But there's a quieter truth waiting beyond the edge of Earth's protection. Out there, the universe doesn't fight our engines first, it fights our biology. Because the human body is not a generic payload, it is a living, repairing, fragile system built for one very specific place, one atmosphere, one gravity, one magnetic field. And the moment we step beyond Earth's magnetic shield, we don't just leave home, we leave the environment that quietly kept us alive. NASA puts it plainly. Beyond low Earth orbit, space radiation can raise risks for cancer, central nervous system effects, and degenerative disease. That sentence is clinical, but the reality it points to is not, because in deep space, the threat is not a single dramatic event, it's the slow erosion of a living body over time. And time, our only true currency, keeps spending itself whether we feel it or not. On Earth, we live inside layers of protection we rarely think about. The atmosphere absorbs, the magnetosphere deflects, even the ground beneath our feet helps. But beyond Earth's magnetic field, the radiation environment changes in character. It becomes more constant, more inescapable. NASA describes two major sources: galactic cosmic rays, high-energy particles that arrive from beyond our solar system, and solar particle events, sudden storms of particles from the sun. And the danger here isn't only the dose, it's the type. Some of these particles carry such high energy that they don't behave like a simple X-ray in space. They plow through matter, they fragment materials, they leave complex damage tracks in tissue. This is why radiation is repeatedly described as a central risk for deep space missions. NASA has even formalized the reality of this constraint in policy. A recent NASA technical paper notes the agency adopted a career radiation exposure limit of 600 millisieverts, tied to a 3% cap on excess risk of cancer-related death above baseline. 600 millisieverts is not a cinematic number, but it's a hard boundary that quietly shapes everything we can attempt. Because once a human body reaches its permissible limit, go farther becomes do harm. And this is where the story gets uncomfortable. Propulsion might get us out there, but radiation decides how long we can stay out there without paying with our future. Imagine this. Picture standing outside at night, under a perfectly black sky. Now imagine a rainstorm is falling, but the drops are invisible. You can't hear them, you can't feel them on your skin, but every drop that lands leaves a tiny cut in the material of your body. Not enough to notice in a minute, but enough that, over months, the fabric begins to fray. That's what deep space radiation feels like in the cruelest sense. Not dramatic, not loud, just relentless, and it keeps falling. Radiation is the danger we fear because it sounds like the cosmos. But microgravity is the danger that dismantles us quietly, from the inside. On Earth, your bones are constantly being reminded that they must stay strong. Every step is a signal. Every climb upstairs is a demand. But in microgravity, weight-bearing bones stop receiving the message. NASA's human research references describe it clearly. Astronauts can lose about 1 to 1.5% of bone density each month during missions lasting 4 to 6 months. Another NASA page makes the same truth feel even sharper. For every month in space, weight-bearing bones can become roughly 1% less dense if precautions aren't taken. 1% per month sounds small, but it's not small when it stacks. 6 months can mean a substantial change in bone strength in the parts of the skeleton that matter most when you return to gravity. And it isn't only bone. Muscles, no longer forced to fight gravity, weaken. 2. Atrophy that NASA describes as a core challenge of microgravity. This isn't cosmetic weakness, it's functional. It can reshape how the body moves, how it recovers, how it survives strain. And what makes this truly disturbing is that degradation isn't always evenly reversible. Bone loss can be stubborn, regional, and in some cases incomplete in recovery, depending on site and mission profile. So even before we talk about decades, we have a problem in months. Then there's the third enemy, the one that feels almost like betrayal, the immune system. On Earth, it works invisibly, constantly. But in space, evidence shows immune function can shift in ways that matter. A peer-reviewed study of astronauts found that long-duration spaceflight increases reactivation of latent herpes viruses, alongside changes associated with stress responses. NASA has published and presented immune system findings that include altered plasma cytokines, reduced T-cell function, reduced natural killer cell function, and persistent reactivation of latent herpes viruses as a biomarker of reduced immunity. And NASA continues active investigations of immune changes during long-duration missions, analysing astronaut samples before, during, and after flight. This is not a single symptom, it's a systems shift, a reminder that the body is not only bones and muscles, it is a network of defences that evolved under Earth's rhythms: gravity, day-night cycles, microbial exposure, environmental stability. In deep space, that stability fractures, and the immune system may not behave like it does on Earth. So the obvious response is, shield more, wrap the ship in thicker material, bring more protection. But then the rocket equation returns with its cold logic. Shielding is mass, and mass is cost. NASA's space radiation work has long emphasized that shielding has limits, especially against galactic cosmic rays, the extremely energetic particles that are hard to stop without creating secondary radiation and other complications. A NASA technical report evaluating shielding effectiveness notes that, under risk projection uncertainties, hydrogen-rich materials like polyethylene could not be shown to significantly reduce risk compared to aluminum in a statistically significant way for galactic cosmic ray risk projections, underscoring how complex the shielding problem is. That doesn't mean shielding is useless. It means shielding is not a simple add more armor solution, because deep space radiation is not a single bullet you can block. It's a spectrum of energies and particle types. Sometimes adding material reduces dose. Sometimes it fragments particles and changes the radiation field behind the shield. And every additional layer you add has to be launched, accelerated, and carried for the entire mission. So the ship becomes heavier. The propellant grows, the architecture swells, and eventually the protection we want becomes the mass we cannot afford. This is the cage. The body needs protection, but protection has weight, and weight has consequences. Here's the part we don't feel until we stare at the calendar. In space, risks don't just add, they compound. Bone loss over months becomes fracture risk and recovery uncertainty. Muscle atrophy becomes reduced capacity to handle emergencies, reduced resilience, increased injury risk. immune dysregulation becomes greater vulnerability, altered inflammatory profiles, and signs of latent virus reactivation. Radiation exposure accumulates against a career limit that exists because the long-term risk is real, and the longer we travel, the more of these risks stack up inside one body. This is why multi-decade journeys don't just sound ambitious, they sound biologically hostile. Not because humans are weak, because humans are specific. We are adapted to Earth, and deep space is not Earth. Now place yourself inside the quiet truth. You're months into a deep space cruise. There is no outside walk to clear your head, no air on your face, no gravity to lean on. And you realize the most unsettling thing about long missions. You don't only measure distance in kilometers and miles, you measure it in changes inside your own body. A month isn't just a month. It's about 1% of bone density slipping away in places you once trusted without thinking. It's muscles weakening unless you fight them daily. It's your immune system adapting to a new world of stress, altered rhythms, and strange biology. It's radiation quietly accumulating toward a limit that exists because the damage is not imaginary. And suddenly, the central mystery becomes painfully clear. Even if we can travel far, can we arrive as ourselves? On the International Space Station, we mitigate these effects with an extraordinary support network, exercise systems, medical monitoring, rapid return options, a constant thread of communication, a protective environment that is still, in many ways, tethered to Earth. But beyond Earth orbit, that tether stretches thin, and the body becomes less forgiving as missions extend. NASA's framing of space radiation as a major risk is not rhetorical. It's embedded in mission planning because exposure influences timelines and operational decisions. And NASA's bone risk documentation makes clear that bone density loss can be rapid and clinically meaningful. So the longer the journey, the more the ship must behave like a miniature Earth, not just a capsule, a closed environment that can sustain biology against the slow violence of space. And that creates the next problem, because survival isn't only about propulsion, it isn't only about speed. Survival is about systems. Systems that can recycle air, recycle water, recycle food, maintain stability for months, then years, without rescue. Because out there, the mission isn't simply to reach a destination, it's to keep a fragile human organism functioning the entire time. And that's why the next truth is unavoidable. Survival requires more than propulsion, it requires systems. We can talk about engines for hours. We can argue about thrust and efficiency and the elegance of nuclear heat. But in the end, propulsion only answers one question. How do we move the ship? Deep space asks a colder question. How do we keep the people inside it alive without Earth? Because in orbit, we can pretend the station is independent, but it isn't. Not truly. It is supported by an invisible supply chain. Launches, spare parts, ground teams, replacement hardware, emergency contingencies. Beyond Earth, that chain snaps, and then life support stops being a convenience. It becomes the mission, a closed system, a miniature planet built out of metal, plumbing, chemistry, biology, and fragile assumptions. And the moment we try to scale that system from months to years, something unsettling happens. The spaceship starts to feel less like a vehicle and more like an ecosystem that must not break. A closed-loop life support system is a simple idea with terrifying consequences. It means we stop treating air, water, and food as consumables we can keep replacing, and start treating them as resources we must continuously reclaim. Air must be scrubbed and refreshed. Water must be captured, purified, and reused. Waste must stop being waste. Because in deep space, throw it away and resupply later is not a plan. It's a fantasy. NASA's work on life support makes this reality visible in the way the International Space Station operates today, where systems are designed to recover and recycle water and to generate oxygen from water. But even on the station, it isn't perfectly closed. It is a hybrid, a partial loop with resupply as a safety net. Deep space removes that safety net, and that is where the story becomes brutally logistical. Water is life support's most haunting variable because it hides everywhere. We drink it, we rehydrate food with it, we wash with it, we sweat it into the air, we breathe it out, and in a sealed habitat, water doesn't disappear. It migrates, it condenses, it contaminates, it becomes a system problem. On the International Space Station, NASA describes the water recovery system as capable of recycling about 90% of the station's water. That number already sounds almost miraculous. But then NASA pushed further. In 2023, NASA described a milestone enabled by the brine processor assembly, raising total water recovery to 98%. 98%. That's the difference between a mission that needs a constant stream of resupply and a mission that can almost carry its own river. Almost, because almost closed still leaves a leak, and over years, even small leaks become mission-ending. A closed system is not only about recycling, it's about how long it can recycle without failing. Oxygen is the most intimate technology we will ever rely on. We can't store enough of it for long missions without turning the spacecraft into a tank, so we generate it. On the ISS, NASA's oxygen generation assembly works by electrolyzing water, splitting it into oxygen and hydrogen. This is elegant, and it's real, and it works. But it reveals a deeper dependency. If oxygen comes from water, then oxygen reliability is tied to water reliability, which is tied to filtration, pumps, sensors, seals, microbial control, maintenance schedules, and the quiet violence of wear. In a closed system, nothing stands alone. Everything is chained. Carbon dioxide is what makes the sealed habitat feel claustrophobic in a purely physiological way. We exhale it constantly. And in a closed environment, it rises unless we remove it. That removal isn't optional, it's life or death. So spacecraft use scrubbing systems, sorbents, fans, valves, thermal cycles, and when you run these systems for days, the challenge is engineering. When you run them for months, the challenge becomes reliability. When you run them for years, the challenge becomes something darker, maintenance logistics in an environment where you can't call for help. NASA-linked research on long-endurance human spaceflight describes exactly this. The maintenance logistics challenge of being farther from Earth with limited resupply and abort options. This is where the romance of exploration meets the reality of spare parts. Imagine this. Picture your home sealed shut. No windows open, no trash pickup, no plumbing connected to a city, no grocery store, no tap. Just you, inside, with everything you need and everything you will ever have. Water you spill doesn't vanish, it becomes humidity. Food scraps don't disappear, they become microbes. Air you exhale becomes a chemical problem that grows by the hour. Now stretch that from a day to a year. That is what closed-loop life support demands. Not heroism, not inspiration. Systems that quietly work without fail. Water and air can be cycled through machines. Food is different, because food is not one substance. It's calories, macronutrients, micronutrients. It's variety for psychological stability. It's shelf life. It's packaging waste. It's storage volume. It's the slow decline of nutrition over time if you rely only on preserved supplies. This is why fully closing the food loop is one of the hardest unsolved practical problems in long-duration human spaceflight. We can recycle water with high efficiency. We can generate oxygen from that water. But recycling food means something much closer to agriculture, bioreactors, or integrated biological systems. Systems that can introduce their own risks, like contamination, instability, and complex control challenges. The deeper we go into closed-loop life support, the more life support starts to resemble life itself, not a machine, an ecosystem. Here is the strange part. A life support system doesn't have to fail dramatically to kill a crew. It only has to fail persistently. A sensor drifts, a pump loses efficiency, a filter clogs, faster than expected. A microbial film grows in a place you can't easily access. A seal degrades. A valve sticks. In orbit, you can resupply. You can swap hardware. You can troubleshoot with an army on the ground. Deep space strips that away. And the academic and NASA engineering literature has been brutally honest about what this implies. Ultra-reliable closed-loop life support for long missions often demands large numbers of spares and a reliability strategy that comes with a severe mass penalty. In other words, to make the system reliable enough, you may have to carry something like another system's worth of replacement parts, and that transforms the mission, because spares are mass, and mass is propulsion, and propulsion is the rocket equation waiting to punish you. Now place yourself inside the real version of a deep space mission, not the poster, not the heroic shot, the quiet middle. You are months from Earth. Communications are delayed. Rescue is not an option in any meaningful time frame. And then you notice it. Not an alarm, not a siren, a small trend in a data readout, water recovery efficiency slipping, a trace contaminant creeping upward, a component that's still working, but not as cleanly as it did last month. And in that moment, you feel the central truth of closed-loop survival. In deep space, a small failure is not small. It is a countdown you can't reset. Because the spacecraft is not just your ride, it is your atmosphere, your river, your lungs, your kidneys, and every imperfection grows teeth over time. So we do what engineers always do. We add redundancy, backup pumps, secondary scrubbers, extra filters, alternate valves, more sensors, spare electronics, maintenance tools, training, procedures. And redundancy is beautiful. It's also heavy. NASA engineering work on deep space life support has spelled out this trade clearly. Recycling systems with sufficient redundancy can meet reliability needs, but they often don't save mass, compared to mixed storage and recycling approaches, because the redundancy itself becomes so large. This is the core irony. To survive far from Earth, we need closed-loop systems. But to trust closed-loop systems, we must carry enough backups that the mass and complexity rise again. And complexity is its own form of risk. More parts, more interfaces, more failure points. The system becomes resilient, and yet more brittle in aggregate, because there are more ways for something to go wrong. This is why long-distance human missions don't scale the way we wish they would. In science fiction, you add distance, and the ship simply travels longer. In reality, adding distance adds time. Time adds exposure. Exposure adds health risk. Health risk demands more countermeasures. Countermeasures add mass. Mass demands more propulsion. Propulsion architecture adds complexity. Complexity adds failure modes. Failure modes demand more redundancy. Redundancy adds more mass. And the loop tightens. Closed-loop life support is a requirement, but it is also a multiplier. The farther we go, the more the mission becomes dominated by logistics and reliability, not by exploration. This is why NASA and research communities talk about long-endurance human spaceflight as a maintenance and logistics challenge unlike anything humans have attempted. Because when you take away resupply and quick return, you are no longer just traveling. You are living, fragile, inside a machine that must behave like a world. So what have we learned? Life support is not a box you pack into a spacecraft. It is the hidden architecture that decides whether distance is even meaningful. On the ISS, we see what's possible. High water recycling, oxygen generation from water, and an evolving ecosystem of machines that can keep humans alive for months and years. with Earth still nearby as a safety net. But deep space demands more than performance. It demands endurance, autonomy, repairability, system that can be maintained without rescue. And once we stare at that honestly, we feel the next truth arriving. Because the moment life support becomes the center of the mission, distance stops being a matter of propulsion alone. It becomes a matter of supply chains, replacement parts, stored reserves, failure probabilities, and the slow mathematics of survival. And that's when distance meets its final opponent. Not physics, not ambition, logistics. Distance now meets logistics. There's a moment, quiet, almost invisible, when the solar system stops feeling like a neighborhood and starts feeling like an ocean. Not because the planets get stranger, not because the light gets dimmer, but because time begins to stretch in every direction. Out here, distance doesn't just separate places. Distance separates moments. And that is where our question sharpens into something uncomfortable. How far can we go before our life runs out? Inside a city, we measure distance in steps. Between countries, we measure it in hours. But the solar system is built on a scale that breaks ordinary intuition. So astronomers use a unit that sounds gentle, but hides something enormous. An astronomical unit, an AU, is the average distance from Earth to the Sun. It's defined precisely as about 149.6 million kilometers, which is about 93 million miles. That's one astronomical unit. And suddenly the solar system becomes a line of numbers that we can actually hold in the mind. Mercury is about 0.39 astronomical units from the Sun. Earth is 1 astronomical unit. Mars is about 1.52 astronomical units. Jupiter is about 5.2 astronomical units. Saturn is about 9.5 astronomical units. Uranus is about 19 astronomical units. Neptune is about 30 astronomical units. Those numbers look clean, but they hide the true horror of scale, because 1 astronomical unit is already bigger than almost every human feeling of far. If you could lay 1 astronomical unit across Earth like a ribbon, it would wrap around our planet nearly 3,700 times. And yet, in solar system terms, 1 astronomical unit is just the first tick mark. To feel the solar system properly, we need a second ruler, one that doesn't measure space. It measures delay. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers, or about 5.88 trillion miles. And in astronomical units, 1 light year is about 63,241 astronomical units. That number matters because it reveals something humbling. Even Neptune, 30 astronomical units away, is not far in light years. It's a tiny fraction, which means the solar system is not a wide empire of space. It's a small island inside a much larger darkness. But even small islands can kill you if the water between you and shore is deep enough. Imagine you're standing outside at night on a long, empty road. There's a streetlight behind you. That's the sun. You can still see it, still feel the faint warmth on your skin. Now you start walking away. At first, it feels normal. The light follows you. Your shadow still makes sense. But then the road keeps going, and slowly the streetlight stops lighting the road and becomes just a bright point behind your shoulder. That shift is what happens as we leave the inner planets and push outward, past Mars, past the asteroid belt, into the realm where the sun is no longer a presence, only a reference, and then the real problem appears. Out there, we don't just travel through space, we travel through delay. Inside Earth orbit, distance still feels controllable. Signals move quickly, mission control feels close, but past Mars, something changes. Not because the radio stops working, it keeps working, but because radio is trapped by the same universe we are trapped by, the speed of light. NASA uses a phrase that sounds clinical, almost harmless: one-way light time. It means what it sounds like, how long a radio signal takes to travel one direction. Now listen to what outer solar system really means in that language. A mission around Jupiter can involve signal delays measured in tens of minutes. For example, NASA's Juno press materials note a one-way light time of about 48 minutes from Jupiter to Earth at that moment. That means if Jupiter goes silent, we don't discover it instantly. We discover it almost an hour later. And Neptune? NASA describes a reality that is almost impossible to feel emotionally. Light from the Sun takes a little over 8 minutes to reach Earth, and about 4.5 hours to reach Neptune's orbit. 4.5 hours. So if you were out near Neptune and you whispered into the void, "Do you copy?" Earth would hear your voice long after lunch had ended, and your reply would not return until night. This is not just engineering, this is isolation written into physics, and that isolation becomes a boundary long before we hit a wall of rocks. Now we confront the bluntest question of all. Even if we had a crew ready, even if we had a ship ready, even if we had perfect courage, how long would it take to actually reach the edges of the solar system? To answer that honestly, we don't use dreams, we use records. NASA has stated that Apollo 10 set the record for the highest speed attained by a piloted vehicle, about 24,791 miles per hour, which is about 39,897 kilometers per hour. That's astonishing. It means those astronauts were moving fast enough to cross the continental United States in minutes. But here's the strange part. In solar system terms, that speed is still gentle, because the outer solar system is not built to be crossed quickly. It's built to expose the weakness of any creature that counts its life in decades. Let's translate that Apollo 10 speed into something we can feel. At about 40,000 kilometers per hour, you cover roughly 1 million kilometers per day, give or take. Now look at Neptune. Neptune orbits at about 30 astronomical units from the Sun. Earth is 1 astronomical unit. Even if we pretend, purely to feel the scale, that we could travel outward like an arrow, we're talking about a difference on the order of 29 astronomical units. And 1 AU is about 150 million kilometers, about 93 million miles. So we're not talking about far, we're talking about billions of kilometers. At the fastest speed humans have ever experienced, the outer planets stop being destinations and become eras, years, a decade, more. And that's before we add the real complications: launch windows, planetary alignment, braking, life support, radiation, return fuel. This created a bigger problem. Distance isn't what kills the mission, time does. When people imagine the edge of the solar system, they often picture a border, a wall, a last planet. But the solar system doesn't end like a country. It ends like a sound, fading. First come the outer planets, then the Kuiper Belt, an immense band of icy bodies beyond Neptune, and beyond that, the Sun's influence continues in a different form, the heliosphere, where the solar wind still pushes outward against interstellar space, and beyond even that, the Oort cloud, an enormous distant reservoir of icy objects so far away that it barely feels connected to the Sun at all. NASA's own description of light, reaching Neptune's orbit about 4.5 hours, is a reminder that by the time we're even at Neptune, we're already living inside a kind of delayed universe. And if we talk about the Oort cloud honestly, we're talking about distances that can reach thousands, even tens of thousands of astronomical units, so wide that the Sun becomes just another star in the sky. At that point, one lifetime isn't a constraint, it's a verdict. Here is the uncomfortable truth we keep running into. Even if we had a crewed ship that could leave Earth at our highest achieved human speeds, the outer solar system would still demand something we cannot easily manufacture: time we do not have. And every attempt to shrink that time runs into the same monster: energy. Because to move faster in space, especially carrying humans, means carrying the systems that keep humans alive: air, water, food, radiation protection, redundancy, spare parts. And every kilogram of that life becomes a demand for propulsion, which becomes a demand for fuel, which becomes a demand for mass. And mass is not forgiving. Mass is exponential consequence. So the outer planets aren't just farther in kilometers. They're farther in the currency that matters most, the currency of mass and the currency of years. There's a particular kind of silence out there, not the silence of no sound. Space is always silent, the silence of no immediacy, no quick help, no fast conversation, no easy return. Picture this for one moment. You're on a ship far beyond Saturn. The sun is still visible, but it no longer dominates your sky. It's just the brightest star behind you, and your world is no longer Earth with distance. Your world is a bubble of metal, heat, and breath, moving through a cold geometry that does not care about your heartbeat. You could still be alive, you could still be thinking, but everything you do would be separated from humanity by delay, and that delay would only grow. This is why the outer boundary of the solar system isn't defined by ambition, it's defined by endurance. When we measure the solar system in astronomical units, it feels organized, reachable, like a map. When we measure it in light time, it becomes something else, a gradient of separation. Jupiter is tens of minutes away by radio. Neptune is hours away by light. And by the time we imagine ourselves traveling physically to those places, inside one human lifespan, we start to understand what the outer solar system really is. Not a frontier of distance, a frontier of time. And then, inevitably, the next truth rises, harder than the last. If the outer solar system already begins to outgrow a human life, what happens when we step beyond the sun's realm entirely? Because beyond this fading boundary, the universe stops being a solar system story and becomes something far colder. Something measured not in astronomical units, but in light years, and that's when the real distance begins. There's a moment when the solar system stops being far and starts being small, not small in our hearts, small in physics, because beyond the last planets, beyond the sun's fading influence, we enter a kind of distance that doesn't behave like distance anymore. It behaves like time, and time is the one thing a human life cannot manufacture. So when we ask, how far could we travel through space in one lifetime? Interstellar space answers with a silence that feels almost cruel, not far enough to touch another star. Astronomers can say it in one calm sentence. The nearest star system is Alpha Centauri, and the nearest star within it, Proxima Centauri, sits about 4.25 light-years away. 4.25. That number looks small, but it hides the true scale of interstellar space, because a light-year is not a poetic metaphor. It is a measurement. NASA defines it plainly. A light-year is the distance light travels in 1 year, about 5.88 trillion miles, about 9.46 trillion kilometers. Now we let that settle. 4.25 light-years means roughly about 25 trillion miles, about 40 trillion kilometers. Not far, not very far. A distance so large it stops fitting inside the instincts our species evolved to survive. And this is the first crack in the story. Even the nearest star is separated from us by a distance that treats a human lifetime like a rounding error. Imagine this. Picture Earth as a single safe island at night. We can see the lights, hear the voices, feel the ground beneath our feet. Now picture taking one step off the shoreline, not into shallow water, into a black ocean that doesn't end for years. That first step is leaving the solar system, because once we cross into interstellar space, the next shore is not a planet, it's a star, and between stars, the emptiness is not just empty. Here's the strange part. We don't even need pessimism to understand the outcome. We can be generous. We can take the fastest speed humans have ever actually experienced in a crewed spacecraft. Apollo 10 set the record for the highest speed attained by a crewed vehicle relative to Earth, about 24,791 miles per hour, about 39,897 kilometers per hour. That speed is stunning. At that pace, you could cross the entire European continent in less than 6 minutes. You could circle the entire globe in just 1 hour. A trip to the moon would take less than half a day. It feels like the kind of speed that should conquer anything. But interstellar space doesn't care how it feels. So let's do the calm, conservative translation. At roughly 39,900 kilometers per hour, a ship would travel on the order of 350 million kilometers per year. And Proxima Centauri is roughly 4.25 light-years away, tens of trillions of kilometers. Even if we could hold that Apollo 10 speed continuously year after year with no slowing, no course changes, no reality of propulsion, the travel time comes out to roughly about 115,000 years, 115,000. When that number lands, something in us changes, because we start to see the real shape of the problem. The distance isn't simply too far. The distance is longer than the entire span of recorded human civilization. When the Great Pyramid of Giza was built, we were still learning what it meant to be a civilization. That was about 4,500 years ago. At Apollo 10 speed, if we had launched toward Proxima Centauri when the pyramids were new, we would still be less than 4% of the way there. After all of human history, we wouldn't even be out of the driveway. And that's not the whole story, because Apollo 10 was a brief peak, an edge of a trajectory, not a cruising speed meant to be sustained. So the generous calculation is already far kinder than reality, and still, time wins. We can also compare ourselves to the fastest long-running outward journeys we've ever achieved, robotic spacecraft. Voyager 1, according to NASA, is moving at about 38,000 miles per hour, about 17 kilometers per second. That is faster than Apollo 10's record speed. And yet, even at roughly 17 kilometers per second, the travel time to Proxima Centauri is still on the order of 75,000 years. So even if we imagine, carefully, conservatively, that crude technology could someday match probe-like cruise speeds, we are still trapped inside the same truth. Interstellar space is not a trip. It is an era, and we only get one lifetime. So a familiar idea appears in human imagination. If one lifetime isn't enough, what if the ship becomes a moving world, and people are born and die on the way? That concept has a name, a generation ship. But here's the uncomfortable truth. A generation ship does not answer how far we can travel in one lifetime. It changes the question into something else entirely. It asks whether a multi-generational society can survive for tens of thousands of years inside an engineered habitat, without collapse, without fatal system failures, without cultural fracture, without losing the very purpose of the journey. And we must be precise here. That is not a solved engineering problem. It's not even purely an engineering problem. It's biology, psychology, sociology, governance, and long-duration systems reliability, stacked on top of one another for time spans that dwarf all human institutions we've ever built. So generation ships don't make interstellar travel possible within a lifetime. They make it not a lifetime journey at all, which means they cannot count as an answer to our original mystery. They are a different story. And that difference matters, because the emotional weight of we went is not the same as someone thousands of years from now might arrive. Now let's take one honest step into the sensation. You're on a ship that has left the sun behind, not metaphorically, literally. The sun is no longer a presence in your sky. It is just one star among others. And every message you send home is no longer a conversation. It is a historical artifact. Because even inside the solar system, light time becomes hours. Between stars, it becomes years. You don't just drift away from Earth. You drift away from immediacy, away from rescue, away from shared time, and eventually away from the human story you came from. This is why interstellar travel is not only a matter of speed, it is a matter of whether we can accept what the journey does to meaning. So we bring it back to the core claim, and we keep it conservative. The nearest star is about 4.25 light years away. A light year is about 5.88 trillion miles, or 9.46 trillion kilometers. The fastest human spaceflight speed on record is about 24,791 miles per hour, about 39,897 kilometers per hour. Even much faster probe-like outward speeds, about 38,000 miles per hour for Voyager 1, still imply travel times to the nearest star measured in tens of thousands of years. This is the boundary interstellar space enforces. We can send machines, we can send signals, we can send our knowledge outward, but we cannot personally go, not in the way the word go means inside a human life, not with our memories intact, not with our bodies surviving, not with the mission still belonging to the same living person who launched. And when we accept that, the story doesn't end, it deepens, because the moment we realize we cannot cross the gulf ourselves, we are forced to ask what travel truly means. If we cannot personally reach other stars, then what counts as reaching at all? And that's where the meaning of distance begins to change. Distance redefines meaning. We've been using one word like it's simple: travel. We say it the way we say travel to another city, or travel across an ocean, as if the universe will respect the same meaning. But space doesn't, because out there the word travel splits in two. One path belongs to machines, the other belongs to bodies, and once we separate those two paths, the story becomes painfully clear. A robotic probe can do something that feels almost supernatural. It can cross decades without aging. It can drift through radiation without fear. It can sleep through silence. It doesn't need air. It doesn't need water. It doesn't need warmth that feels like home. It only needs power and time. That's why robots can go where we cannot. Not because they are braver, because they are not alive in the way we are alive. But humans don't travel as data. We travel as breathing organisms, with fragile chemistry inside our blood, and fragile thoughts inside our minds. And that difference changes everything. Because for us, distance is not only measured in kilometers, it's measured in what it does to the body and what it steals from the self. Here's the strange part. When we imagine going somewhere in space, we usually picture arrival as a physical event. A ship slows down, a window fills with a new world, boots touch alien ground. But human travel has a deeper requirement. We must arrive as ourselves, not just alive, but coherent, with memory still intact, with health still stable enough to experience the place we fought to reach. Otherwise, what did we do? We didn't travel, we merely endured. So for a human life, travel quietly carries three invisible demands: return, health, memory, and each one is a knife. Return is not sentiment, return is definition. If we can't come back, or at least keep the option open, then the mission changes shape. It stops being a journey. It becomes exile, and exile can be heroic, but it is not the same thing as travel, because travel implies we still belong to the world we left, that we can reconnect, that the story can close. But deep space stretches return into something that doesn't fit inside a single life. So even when we talk about how far can we go, the honest question is harsher. How far can we go and still have a life to return to? Our body does not care about mission patches or speeches. It cares about radiation, about bone, about muscle, about immune function, about sleep, about stress, about isolation. The body keeps time in ways that are indifferent to our ambition. That's why long-duration travel is not only a matter of reaching a destination, it's a matter of arriving with a body capable of standing, thinking clearly, functioning, surviving. Because an arrival you cannot live through is not an arrival, it's a tragedy. Then there is the quietest requirement, the one we almost never say out loud: memory. A human life is not just a biological sequence of breaths. It is a continuous thread of identity, a story we carry from childhood to whatever comes at the end. But extreme distance can fracture that thread, not only through time, through separation, through delayed communication, through the slow erosion of shared reality. If the people you love are years away by radio, then the relationship changes, not because anyone wants it to, because physics forces it to, and with enough time, even language can drift, even culture can drift, even the emotional center of your life can drift, until Earth becomes less like home and more like a legend. So when we say travel, we must confront a question that feels almost philosophical, but is actually practical. Can we still be ourselves that far from our own world? Imagine this. Picture writing a message to someone you love. Not a long letter, just a simple line. I miss you. Now picture dropping it into a mailbox and knowing it will arrive years later. Not because anyone is slow, because the universe is, and by the time it arrives, the person who reads it is older, different. The moment you wrote about is gone, and the reply, if it comes at all, will return to you long after you needed it. Now ask yourself what that does to the human experience of a journey, because travel isn't only moving through space. Travel is remaining connected to meaning while you move. An interstellar distance attacks meaning at the roots, so we have to say it cleanly. Robots can explore, humans can be present, and those are not the same achievement. Robotic exploration is extraordinary. It extends human knowledge beyond human reach. A probe becomes our eyes, our instruments become our senses, and in that sense we have already reached places that no human body can survive. But human presence is different. Presence means the place touches us back. It means we see it with our own eyes. We feel the time pass in our own chest. We remember the moment not as a data packet, but as lived reality. Presence is not superior, it is simply different, and it is far more expensive. Because presence demands life support, shielding, redundancy, psychological stability, error tolerance. Presence demands that we carry a small world with us, and a small world is heavy. Now let's make this painfully personal. If you leave Earth for a mission that lasts decades, and you spend most of that time in confinement, in monotony, under constant risk, what returns? Not your name on a report. You, your mind, your memories, your sense of time, your sense of belonging. And if the journey breaks those, even if the ship arrives, did you arrive? Or did something else arrive wearing your body? This is why scientists and mission designers don't only argue about propulsion and trajectories, they argue about what the human organism can endure without losing the very thing the mission was meant to protect: a living, thinking, remembering person. This is where our story cracks open. Because once we accept these limits, the universe forces a different idea of exploration. The heroic fantasy is always individual. One ship, one crew, one lifetime, one triumphant arrival. But the real human pattern is rarely like that. Real exploration has almost always been collective, built on generations of knowledge, institutions that outlive individuals, tools and methods that improve slowly, and countless unnamed contributions. Even our biggest space missions are not the act of a single person. They are the act of a civilization concentrating effort. So maybe the deepest truth is this: when we explore the universe, we are not extending one life. We are extending a shared human continuity, and that continuity can reach farther than any single body, because it isn't limited to one heartbeat. It is limited only to whether we keep building, whether we keep remembering, whether we keep caring about the questions, So what does travel truly mean for a human life? It means more than crossing a number on a map. It means going somewhere and being able to experience it as a human being. It means the journey does not erase the traveller. It means arrival still contains awe, clarity, memory, something we can bring back into the human story. And if we strip away fantasy, we're left with a sober conclusion that doesn't end the wonder. It refines it. There are distances we can reach with machines, and there are distances we can reach with our bodies. And the gap between those two is not failure. It's a definition of what we are. We are not built for the deep void. We are built for meaning, for connection, for air and warmth and time that feels human. And that leads us back, not forward. Back to the question we started with. Not how far can something travel, but how far can we actually travel in one lifetime? We can finally say it, clearly, simply, without romance. In one human lifetime, the farthest place we can realistically travel as living humans is not another star. It is not even the outer planets. It is the small, brutal, beautiful neighborhood of space where our biology can still survive and our time can still matter. Earth, the moon, Mars. That is the true boundary of a human life in space. Not because we lack imagination, because the universe does not negotiate with time. When we ask, how far could humans actually travel through space in one lifetime? We're really asking a more intimate question. How far can we go and still remain human, still return, still remember, still stand there and feel it? And the honest answer is this: we can move beyond Earth. We can reach the moon reliably within days. We can reach Mars with enormous effort within months. But beyond Mars, the travel times, the risks, and the human cost begin to stretch past what a single life can responsibly carry. So the maximum distance isn't just a number, it's a region, a sphere of reachable worlds defined by fuel, biology, and the ticking of one heart. Let's anchor it in distances we can actually feel. The moon is about 239,000 miles, about 384,000 kilometers from Earth. That's far enough that the ocean between us and home becomes an invisible curve, but close enough that a human can still go and come back within a fraction of a year. Mars is different. Mars is not one distance. It is a moving target in a moving dance. At its closest, Mars can be roughly 34 million miles, about 55 million kilometers away. At its farthest, it becomes hundreds of millions of kilometers away, so far that the idea of near starts to break. And that's the point. The moon is a step. Mars is a migration across emptiness. Mars forces us to live inside time. A typical journey to Mars with the kinds of trajectories mission planners actually use is measured in months, not days. Not because we're slow, because the solar system is a machine and we ride its gears. And even that human sphere, Earth, Moon, Mars, demands almost everything we have. It demands engineering, it demands planning, it demands discipline, and it demands a kind of humility that is rare in a species that dreams in infinite horizons. Imagine this. Picture a dark room with 3 small lamps. One lamp is warm and bright, close enough to read by. That's Earth. Another lamp is farther away, still visible, still reachable with an outstretched arm if you were long enough. That's the moon. And the third lamp is across the room, dimmer, smaller, and separated by empty air you cannot swim through. That's Mars. Now imagine trying to reach a 4th lamp. To find it, you wouldn't just leave the room. You would have to walk out the door, cross the continent, and look for a light on the other side of an ocean. That's the nearest star. The difference isn't a bit farther. It's a different category of reality. So, our reach, the reach of a human body, lives in that dark room, and within it, Those 3 lights are the distances we were always meant to take seriously. Here's the strange part. Limits usually sound like failure, but in science, a limit is often a form of clarity. A limit tells us what is real. It tells us what costs something. It tells us what matters enough to pursue anyway. Because if we could go anywhere with ease, then going would mean less. If every horizon were reachable, then no horizon would feel sacred. But the universe doesn't give us that kind of freedom. It gives us something harsher, and maybe more meaningful. It gives us a boundary. And inside that boundary, every kilometer becomes a decision. Every mission becomes a moral question. Every launch becomes a statement about what we value. We should be honest. The cosmos does not care about our scale. The Milky Way is still vast beyond comprehension. The nearest star is still too far. For human life to touch, the universe remains what it has always been, ancient, indifferent, and unimaginably large. But something changes in us when we accept that, because the purpose of exploration was never to conquer space. Space can't be conquered. The purpose was to understand our place inside something that dwarfs us, to extend our senses, to refine our questions, to make the darkness less mysterious, not by denying it, but by learning its rules. So the truth isn't that we are small. The truth is that we are precise. We are fragile beings who can still reach outward with astonishing intelligence. We build instruments that see back in time. We build spacecraft that outlive their creators. We translate the language of atoms into maps of galaxies. And even if our bodies can't cross the gulf to the stars, our understanding already does. And now, just for a moment, place yourself inside the real achievement. You are not imagining a starship crossing light years. You are imagining something more honest. You are standing on the surface of the moon and Earth is hanging in the sky, a blue-white marble, silent, whole. Or you are standing on Mars, under a thinner sky, watching dust move like weather from a world that never became ours. In that moment, the distance is not an abstract number. It's the realization that you carried your life across a gap that nature never intended you to cross. And you did it anyway, not by magic, by discipline, by math, by human cooperation, by a civilization choosing together to reach beyond its cradle. That is not small. That is staggering. So, we return to the original question, and we let it land with full weight. How far could humans actually travel through space in one lifetime? Far enough to leave Earth, far enough to touch the moon, far enough to reach Mars, not far enough to escape time, not far enough to outrun biology, not far enough to personally cross the interstellar gulf, but far enough to do something profound, to turn a species that once feared the night into a species that measures it, to turn the sky from a myth into a map, to prove that even with short lives, we can still participate in cosmic truth. And this is where the story becomes calm, because maybe the point was never to go everywhere. Maybe the point was to understand what it means that we cannot, to accept the boundary, not as a prison, but as a frame. Because a frame gives shape to meaning. A frame makes the picture matter. We spend so much of our lives pretending time is negotiable. We act like we can save it, stretch it, hide it in calendars and routines, as if one more week, one more year, one more decade is always waiting somewhere ahead. But the universe doesn't share that illusion. Out there, time is not an idea, it's a wall. It's the one law that touches everything we love. And maybe that's why space moves us so deeply. Not because it promises escape, but because it forces honesty. When we stare into the black between worlds, we're not just looking at distance, we're looking at the shape of our own limits. The truth is, we will never be creatures made for endless travel. We are creatures made for warmth, for air, for familiar voices, for places that hold our memories like fingerprints. We belong to a small world, and that should feel tragic. But then, something quieter happens, because once we accept how narrow our reach really is, we begin to understand what a miracle it is that we reach at all. A fragile species, built from water and breath, able to measure stars, predict eclipses, decode light that left its source before our ancestors had names. We cannot cross the universe in one life, but we can give one life to the universe. We can turn curiosity into instruments, fear into planning, loneliness into shared purpose. And when we do, the cosmos doesn't feel like a cold place we're locked out of. It feels like a truth we are slowly learning to hold. Maybe meaning was never waiting at the edge of space. Maybe it was always here, in the fact that we look up, and something inside us refuses to stop. Our bodies may be brief, but our questions are not. And that is how we travel, not by outrunning time, but by leaving behind understanding that time cannot erase. So when the night sky feels too vast, too indifferent, too far to touch, remember this: we don't need to reach everything to be changed by what we see. Our reach is short, but our understanding is vast, and in that vastness, we are not lost.